Okay, back to the literature. How does our analysis fit, for instance, with Stokey and not to mention Shapiro and Walker? So to tackle that question, I'm going to use the paper again. So let me just set that up. Okay, so what I'm going to do is draw the PPF. So what do we have? We had P and X, but now I'm going to draw in intensive form. So that could be, I think in my paper that ALL, that would be A, right? That's effective labor inputs. So this is consumption per effective labor input. This is polluting emissions per effective labor input. Okay. And in my paper, if we assume that there's no perfectly clean production possible, like the coal example, or if we think of the big picture, we can never produce without some compromises for the environment. If we assume that that's true, the PPF might look something like this, right? And that's in intensive form. When ALL is small, in normal form, X and P, it would have like this, then like this, then like this, then like this, then like this. But if we divide by ALL, even as ALL grows, the PPF just stays where it is. Okay? And what about in Stokey, or indeed in Shapiro and Walker? If again we use the same notation, which is not the notation used by Stokey or probably Shapiro and Walker, I guess, I don't remember right now. What does their PPF look like? It's actually the same. It's basically, if you think of the Cobb-Douglas, remember the picture we drew before, the more pollution you use or that you allow yourself to emit, the more you can produce, starting at zero and then increasing, but at a slower and slower rate. But then you hit the buffers at some point. Okay, but before, it's not terribly clear here, but because I haven't drawn it very well, but before it's leveled off completely, right? It never actually levels off completely. So yeah, should have drawn it like that. Okay, so that's the PPF. If you like, if you want to complete it, you could almost draw it like that. Okay, so increasing pollution helps production up to a point at which that is like you hit this corner and then you don't get any more. So the PP production possibilities are within this area. Yeah. Okay, so how does our analysis fit with Stokey, not to mention Shapiro and Walker? So they just sort of posit this rather unintuitive function, whereas we start from a model with a sort of pollution generation process and sort of endogenously generate this shape. Okay. In terms of what happens, if we stay in intensive form and look at the indifference curves, if we think of ALL being very low, then X is also very low. Even when we're up here, we're consuming very little. The indifference curve is almost flat. Okay. I'll try doing it in red, see if it shows up. It curves up very slightly. Oh, that's not showing up. But it's pretty much flat. We're very poor we have pretty good environment. P over ALL is also very low. Sorry, P is very low because ALL is low. So we have very little pollution and very little consumption. We have great environmental quality because remember, P is going up this way, but Q is going up this way. When ALL is very low, we have great environmental quality, very little pollution, but very little to eat. We hardly care about environmental quality, we just want to maximize our consumption. But as ALL goes up, in intensive form, this indifference curve steepens and we shift round like that. So here's an indifference curve later on with the optimal point. Okay, and we start, that process starts from the word go, assuming that the optimal taxes are imposed. Even when consumption is very low, there's still going to be some very low level of tax and some slight shift away from this top point. Okay, so gradually we'll shift more and more. By the way, you might think this looks like we're heading for zero pollution, but we're not necessarily. Even if this red dot is heading for the origin here, this is P over ALL. And ALL is going to infinity. So even if the red dot moves towards the origin, P could still be growing. Okay, and that's where this trade-off between the eta and the sigma kicks in. Right? Whereas, if instead we had a ppf that looked like that, right, hitting the y-axis, then we would definitely, as the indifference curves got steeper, we would definitely get to this point of literally zero pollution. We would hit zero. If there's a clean technology out there, however expensive it is, if we keep growing, we will eventually choose it. Okay, so that's our model. What about, how do we interpret Stokey or Shapiro and Walker in these terms? Well, initially the indifference curve is almost flat, and oh, we've got a strictly positive slope of the black line here, so literally nothing happens, we're at the corner. And even though the indifference curve may have got significantly sloped, but still we're at the corner. So there'll be a period where we're at the corner and pollution increases. But then finally, at some point, the indifference curve will get steep enough that we start moving away from the corner, moving around here. Okay. And in the sort of Cobb-Douglas, in the case when eta equals sigma, we will move around at just the right rate to keep P constant. Okay. P over ALL goes down, but P will be constant. But apparently, according to the analysis of Shapiro and Walker, the shape of the curves is such that actually we move around faster than that. But of course, you have to think of it like econometrics. When you read the Shapiro and Walker, they assume that this functional form is true and then fit it as well as they can to the data. And if you look closely at their paper, they say that I can't remember exactly how they word it, but they sort of say, oh, we assume that we're never at the corner. We assume that there's always some abatement. Okay. So, how does our analysis fit? It's closely related, but far more general. Okay. What about Andreoni and Levinson and Brock and Taylor? Well, it's completely different. Okay. So we assume unbiased technological change, and that the pollution reductions are driven by the increase in willingness to pay for a clean environment. Both Andreoni and Levinson and Brock and Taylor, they assume biased technological change, not driven by incentives, just exogenously biased, that abatement gets cheaper and cheaper over time, and therefore, even though willingness to pay for a clean environment stays the same, we abate more and more and head for zero pollution. There's not a lot of evidence for that view. Okay. Right, that was that.